Hey, this is Kevin. Welcome to the channel. I'm a first year math major, econ minor at Reed College. And starting from today, I hope to upload more videos more actively on contents from Math 112, Intro to Analysis, Math 201, Linear Algebra, and Econ 201, Intro to Economics. These are three of the four classes I'm taking in the fall semester right now. And um, I'll just be uploading problems or problem sets, mostly just specific problems because problem sets are too long to cover in one setting. But yeah, at least that's the goal. That's the goal. I find it tremendously rewarding to be able to walk through the problems again and explain it to others, and also just teach it to myself one more time, which is a great way to truly check if you've understand the material, and also a really helpful way to prepare for the final. So before diving into any specific problem sets, I do want to tell you a little bit about this very nice lemma that we proved in my linear algebra class a few weeks ago. The name of the lemma is called the exchange lemma. So the exchange lemma, which basically just states, if I have a basis for a vector space, which the vector space has to be finite dimensional. So if I have a basis, so let V be a vector space over a field F in finite dimensional. Then, let's say the basis is little v, v1, v2, and v3. I can replace one of the three elements, but the key word here is one at a time. I can replace any one of these elements one at a time to some different elements, as long as the coefficients in front of v1 in the replacement of v is non-zero. That's still going to be a basis. So what I mean by that is, okay, take w, which equals like v1, like a v1 plus b v3, and then still v2, v3. This is still a basis as long as a doesn't equal to 0. It's still a basis as long as a doesn't equal to 0. Which makes sense intuitively, because if a were to be 0, then you're losing your a1, right? Then what you have left would just be some linear combination of those two elements, which will make the set linearly dependent, which will not be a basis. So what I have on the board here is just me going over problem 4, which is the problem that I did wrong on one of the most recent exam. So problem 4 states, let V be a vector space over F and U, V, and W distinct vectors in V. So prove that if the set U, V, W is a basis for V, then U plus V plus W, comma, V plus W, comma, W is also a basis for V. Let's see. Yep, yeah, the whole board is in frame, so that's good. So by exchange lemma, right, which states we can only replace it one at a time, so we're going to replace it one at a time. So here we're replacing the first U by U plus V plus W, since it is very obvious that the coefficient of U in U's replacement is not 0, so this is still a basis. And after that one, I'm now replacing V with V plus W. The goal is to get the basis from here to look exactly like that, and then to show that it's still a basis. And we're doing that one at a time. Like I'm not replacing two at the same time. I'm doing that one here, like one step here, and then the other step here. So now we're replacing v by v plus w. Now we need to show the coefficient in front of v is not zero, and the idea of the whole part of the definition of what it means to be a basis is you're able to express any vectors in the vector space as some sort of a linear combination of the basis elements. So here I'm just rewriting v plus w as some linear combinations of the basis elements in my previous basis. So v plus w is equal to a times the first part, and b some scalars times the second part, and c times the third element. And it's trivial that a is 0, b is 1, and c is 1, right? That's going to give us v plus w, because 1v plus 1w is sufficient to give us v plus w, so a can just be 0. This whole term will just be 0. Since b equals 1, which is now 0, the coefficient of v in v's replacement isn't 0, so this is still a basis. And because this is exactly in the form of that, so therefore, according to exchange lemma, this is still a basis for v. Yeah, I definitely did way too much work than I needed on this problem. I proved exchange lemma basically a second time, but the realization here is understanding the exchange lemma and how to apply it to problems. So yeah, that's definitely really cool, and I hope you like that.